Hi, I'm Ceri Lewis. I'm a marine biologist at Exeter University, and my research focuses on how climate change and pollution affect the health and reproductive biology of marine invertebrates. So that's things like mussels and sea urchins like this. So the oceans cover 70% of the planet's surface, but because they're deep, they actually contain 99% of the living space for animals on our planet. So they contain a large proportion of the global biodiversity. It's about 250,000 species living in the ocean that we know about, but there are plenty that we haven't discovered yet because the oceans are so deep and difficult to explore. But the oceans aren't just important in terms of biodiversity. 1 in every 3 breaths that we take comes from oxygen produced by phytoplankton living in the oceans. So the ocean's health directly affects our health as well. And we also rely on the oceans as an important source of food through our fisheries. So it's really important for us to understand the impact of climate change on our oceans, as it directly relates to us. So my research focuses on the impacts of climate change on marine invertebrates. The marine invertebrates make up the biggest proportion of that ocean biodiversity. They make up 76% of the species in our oceans. And you can see lots of examples of marine invertebrates on a rocky shore like this when the tide goes out. So for example, I have a few here. This is a common shore crab, Carcinus manus, so he's a crustacean. We have some sea urchins, we have some limpets and some little marine snails. There's actually 200 different species of marine invertebrates on this rocky shore alone. And they're very important bottom of the food chain animals. So the impacts of climate change on these guys escalates up the food chain to the fish that we rely on as our food. One of the big focuses of my research at the moment is looking at the impacts of ocean acidification on animals such as these. Ocean acidification is considered by many marine scientists to be one of the biggest threats to ocean biodiversity. So what is ocean acidification? Ocean acidification is often referred to as climate change's evil twin because it's also caused by increasing carbon dioxide levels in our atmosphere. As you've been learning throughout this course, since the Industrial Revolution, carbon dioxide levels in the atmosphere have been increasing, and they're now around 400 parts per million. Now, the ocean plays a really important role in the carbon cycle. Carbon dioxide is really soluble in seawater, and the ocean actually absorbs about 1/3 of that atmospheric carbon dioxide. As it dissolves into the seawater, it causes a series of chemical reactions, which is now leading to ocean acidification. This is how it works. So the ocean absorbs 1/3 of the atmospheric carbon dioxide, and this has always been going on, even before carbon dioxide levels started increasing. So as carbon dioxide dissolves into seawater, it reacts with water to form carbonic acid. This carbonic acid is really unstable and quickly dissociates into 2 ions, bicarbonate and hydrogen ions. And it's the concentration of hydrogen ions in seawater that determine its pH. The pH of seawater at the moment is about 8.1. Now, as carbon dioxide levels in the atmosphere increase, the amount of bicarbonate and also hydrogen ions in seawater is also increasing. However, the ocean has a natural buffering system. It's called the carbonate buffer. Carbonate ions in seawater act as that buffer and soak up those protons, those hydrogen ions, as they're released. And it's that carbonate buffering system that's kept the pH of the ocean stable for millions of years. Carbonate ions enter seawater through natural weathering of rocks such as limestone and also from the shells of dead marine animals. So those processes that put carbonate into seawater are really quite slow processes. Ocean acidification is happening because of the rate at which we're putting carbon dioxide into the atmosphere. We're putting carbon dioxide into the atmosphere and therefore the oceans at a rate which is exceeding the rate at which carbonate ions are being put into the ocean. And so there's less carbonate available now to soak up those hydrogen ions. And this is causing the pH of the ocean to fall. Since the Industrial Revolution, the pH of the ocean has fallen by about 0.1 of a pH unit. Now that might not sound like very much, but actually pH is measured on a logarithmic scale, so that's equivalent to a 30% increase in hydrogen ion concentration in the seawater. And because the ocean has been so stable for so long, that 30% increase in hydrogen ions is a bit of a shock for the marine animals living there. Now, if we continue to release carbon dioxide into our atmospheres at the rates that we're predicting at the moment, we're looking at a pH change of about 0.3 to 0.4 of a pH unit by the end of this century. And that equates to about 120% increase in hydrogen ions. And so we're really worried about what this change in the pH of the oceans means for the animals that live in it. One of the reasons we're worried about ocean acidification is the rate at which it's happening. The pH of the ocean has been stable for millions of years, but it's now changing due to the increased carbon dioxide in our atmosphere at a rate faster than any other time in the last 300 million years. So we're worried about whether the animals living in the ocean are actually going to be able to cope with this change, as it's happening too fast possibly for them to adapt. One of the aspects of ocean acidification that scientists first started looking at was its impacts on calcification. So a large number of marine invertebrates have calcium carbonate skeletons. This oyster, for example, has a really delicate shell which is made out of calcium carbonate, and any shells that you see on a beach are made of this calcium carbonate structure. Other animals, such as sea urchins, also have calcium carbonates in their skeletons. So calcification is the precipitation of calcium and carbonate ions into this solid shell form. Once it's formed, a calcium carbonate structure like this shell is quite vulnerable to dissolution again unless it's surrounded by seawater that has saturated calcium carbonate levels in it. So the saturation state is the thermodynamic potential of any mineral, such as calcium and carbonate, to either form a solid or dissolve. So when the seawater becomes undersaturated with carbonate ions, the tendency is for these structures to start dissolving. As we've learned, when carbon dioxide increases in the ocean, we get a reduction in the carbonate ions because it's soaking up those hydrogen ions, acting as a buffer. So as ocean acidification progresses, the amount of carbonate that's available for these shells to form will start to decrease, but also the ocean will become undersaturated, and we'll see that tendency for shells and structures such as this to start dissolving. So we can do a little experiment now to have a look at this reaction and how reduced carbonates in seawater actually dissolve our shells. I've put my safety specs and my gloves on now because I'm going to use some hydrochloric acid. Now this is pH 1. The ocean is never going to reach pH 1 through ocean acidification. This is just to purely show the chemical reaction that occurs. So I'm going to pour some hydrochloric acid into this beaker. And then I'm going to put my calcium carbonate oyster shell into the acid. What you can see straight away is that it started to bubble off carbon dioxide gas. So what's happening here is the hydrogen ions in the hydrochloric acid, which is a stronger version of what will happen in the seawater, is reacting with the calcium carbonate, and it's forcing it back into the ionic state, calcium ions rather than a carbonate shell, and the carbon dioxide gas is bubbling off the shell. So I've used a strong acid here to show you how increasing hydrogen ions in water can affect shells and cause them to dissolve. But in the ocean, with ocean acidification, the pH isn't going to become strongly acidic like this. The pH is going to fall to about 7.6 by the end of this century if we continue to burn fossil fuels at the rate that we are at the moment. So we're not going to get extreme bubbling of shells like this. It's going to be a much slower process, but it's the same chemical reaction that will be happening over long periods of time for any animals that have these calcium carbonate shells. So in the cold polar waters, such as the Arctic and the Antarctic, where more carbon dioxide dissolves into the seawater because it's colder, we've already got some undersaturated water with respect to carbonate ions. And so we're already finding small marine creatures with calcium carbonate shells showing signs of this dissolution process because of this undersaturation of carbonate ions. So we know that this is a process that is already happening in our marine environment and that will get worse as ocean acidification progresses. Calcification isn't the only process that might be impacted by ocean acidification. That increased carbon dioxide levels in seawater has the potential to alter the basic physiology of any marine organism. All organisms produce CO2 as we respire. It's a waste product of respiration, and we have to get rid of that carbon dioxide in order to prevent our cells becoming acidic in the same way that the ocean becomes acidic when you have increased carbon dioxide. We're very good at regulating our internal carbon dioxide levels. We breathe and respire to get rid of that CO2. Now, any water-breathing animal does the same thing. So some animals are much better at controlling their internal carbon dioxide levels than others. So this crab, he's particularly active, as you can see, he's a fighting crab. He's really good at controlling his internal carbon dioxide levels because he naturally generates a lot of metabolic CO2 by being really active. So he's got a buffering system in much the same way that seawater has a buffering system, in that he can use bicarbonate inside his cells to buffer any acidosis from increased carbon dioxide. A more sedentary animal, however, like this limpet, he doesn't really move around so much, so he's not so well adapted to buffer that increased carbon dioxide from metabolism because he doesn't produce as much of it. So he's much more susceptible to having internal acidosis from ocean acidification because he hasn't got those systems for buffering carbon dioxide inside his cells. So one of the most sensitive part of any animal's life cycle to changes like ocean acidification is when they're reproducing. Now, marine invertebrates, like this sea urchin here, they reproduce by releasing their eggs and sperm directly into the seawater, and fertilisation happens outside of the animal directly in the seawater. So these processes are really sensitive to what the conditions of the seawater are because they're directly exposed to them. And eggs and sperm are really small and much less able to control their conditions inside them, so are more sensitive to any changes happening in the seawater. When fertilisation takes place, an embryo very soon develops into a very small larvae. Marine invertebrates have what we call biphasic life cycles, so they're two distinct components of their life cycle. This is the adult form, but it has a very separate and very different larval form that can spend months living in the open ocean before it then comes back and settles and metamorphoses into the adult form that we're more familiar with. Now, marine invertebrate larvae are known to be very sensitive to any kind of change in the seawater, and there's a lot of ocean acidification studies being done now that show these are the most sensitive stages to ocean acidification. So, for example, sea urchin larvae grow tiny calcium carbonate skeletons which enable them to swim properly and helps them feed. We know from ocean acidification experiments that these calcium carbonate skeletons in sea urchin larvae don't form properly when we're exposing them to the conditions we expect for the end of this century. So less of those urchin larvae are able to grow their skeletons properly, and it means less of them make it to adult phases because they're not feeding properly and they die. So the numbers of urchin larvae that then make it to the adult population become significantly reduced. This has real implications for populations of all marine invertebrates due to the numbers of settling larvae being reduced in ocean acidification conditions. So here at Exeter, in our lovely research aquarium, we're part of a big national programme doing ocean acidification experiments, looking at the impacts of ocean acidification on commercially important shellfish species. So what we have here are some native oysters, and we're taking them into the future 100 years by bubbling air that's at the carbon dioxide levels we're expecting for 100 years' time into the seawater to mimic ocean acidification conditions that we're expecting for the end of the century. And then what we do is we measure their responses to see how they're going to cope. So there are lots of things we still don't know about how animals will respond to ocean acidification. One of the big questions is which species are going to be the most sensitive and which species can actually cope with the changes we're expecting. But another really difficult question to look at is how are animals going to adapt? Is the rate of change of ocean acidification actually too fast for species to cope, or can some animals adapt and evolve and actually be okay in our future ocean? Another important question is how is the change in pH and increased carbon dioxide levels in the seawater going to interact with other stressors? Ocean acidification is not happening in a pristine ocean. It's happening against a background of environmental pollution and chemical contamination. Another question that we're looking at here at Exeter is how is ocean acidification going to interact with chemicals that we know are in the waters around the UK? Many of the invertebrate species that we work on are very important bottom of the food chain animals. So it's really important for us to do research like this in order to be able to understand the knock-on effects both for ecosystems in the marine environment, but also the food that we rely on from the marine environment, such as our fisheries.